There are different types of tests we can perform on a rock sample, and here I list out all of them. So the uniaxial compression test is one, which basically says you do not apply any radial confining stress. So S2 equals S3, which is in the radial direction, and there is zero stress. But you have a non-zero stress in the axial direction. And from that, you can get UCS. We talked about this, and you can get Poisson ratio and Young modulus. Then we have the hydrostatic. And for hydrostatic, it just means the stress in all directions is equal. So the axial stress equals the radial stress. Then we talked about the triaxial compression test, where the stress in the radial direction is different from the stress in the axial direction, and that's the most common test. So S1, which is the axial stress, is greater than the confining stresses. So the confining stresses are the stresses that act in the radial direction, but the axial stress is greater than the radial stress. Then we have this one which I haven't talked about until now, and it is the triaxial extension test. And you see that the arrow still indicates you're compressing. So why is it referred to as an extension test? Well, it's because now you notice the difference. This is S1, this is S3. And you know S3 is the least principal stress. So the moral of the story is that the radial stresses are greater than the axial stresses in the triaxial extension test. So S1 is greater than S2, S3. And S1 is what acts in the radial direction. So when you are applying the greatest stress in the radial direction, then the material gets, so if this was the material originally, and this stress is greater than the vertical stress, so what happens? The material gets leaner, right? But it gets, oh, I can actually change color. So it gets leaner, but it also gets taller, right? We had discussed this concept when we looked at the uniaxial stress and we talked about Poisson ratio. And that was the reverse. In that case, you started out with the blue. Then because the axial stresses was greater, then the material grew shorter, but also grew farther. Here you're starting out with a farther sample and it's going to grow leaner. So the radius decreases, but its length increases. And in that case, it looks like it's tensional in the axial direction. And that's why it's referred to as a triaxial extension test. Whereas the standard triaxial test is a triaxial compression test. So when we talk about the triaxial test without making mention of whether it's extension or compression, it is actually compression, because our oil and gas convention is that compression is positive, and that's what we have in mind. And in that case, the axial stress exceeds the magnitude of the radial stress. And we actually have a true polyaxial test where S1 is different from S2 and different from S3. So recall that in the triaxial test, S2 was equal to S3, right? Because all you're using is a fluid to apply confining stress on the sample. And so you wouldn't be able to account for the true intermediate stress values, right? Because S2 equals S3. S2 is the intermediate stress value, the intermediate principal stress. So to get that, you will need a true polyaxial test where these three stresses are different. But you can already guess that it's very difficult to do this in the lab, which is why we don't talk about it so much. Why? Because you don't have core holders that can fit square samples. The core holders are typically cylindrical. You'll see one on the next slide. And it's just so difficult to actually perform this kind of test. So by far, the most common test is the triaxial compression test. So I summarize those here. Uniaxial stress, not very useful. Why? We talked about this at the beginning of module 3. We have those micro cracks, right? At the beginning when we said you will have a nonlinear behavior when you're looking at stress strain plots, a nonlinear behavior which is reversible. Then you have the true linear behavior, then you have a nonlinear, and you can actually have failure. And this part, we said it was cracks closing, right? And when you have those cracks in your rock, it makes the rock appear weaker than it really is. And that makes rock strength lower. So the uniaxial stress test, the uniaxial test will underestimate the rock strength because it's going to have the micro cracks in it. To close the micro cracks, you need to apply some confining stress, and the triaxial or even the hydrostatic test overcome that because the confining stresses, which are non-zero in these cases, closing the micro cracks, and you can get more realistic estimates of the rock strength. I already talked about this being difficult, this test, because it's difficult to even get cubic core samples. Obviously, we don't have cubic core holders, but this can actually be designed, right? But how do you get a cubic core sample when your wellbore is cylindrical? Your coring device is cylindrical, so you will have to get a cylindrical core from the subsurface, then cut it to this shape, and it's going to be much smaller. And the process of cutting can actually create fractures in the rock that weren't there at reservoir conditions. So, moral of the story is the triaxial compression test is the most common, and that assumes S2 equals S3, which is the radial stress, and so you can't really evaluate the intermediate stress value, which will be S2. Now you see the picture of the triaxial test cell right here. So this is your core sitting in the core holder, and you see this empty space right here. Well, the fluid gets into this cell, and that's how it's able to apply compression test all over the curved surface area of the sample, which is what you're showing here with these arrows. So that's your confining stress. The fluid fills up this and pressurizes it. Then on top of that, through this, which is right here, you are able to apply an axial load. That's your axial stress from top and bottom, and it gives you that compression which you want. And I should point out that this test actually measures or it controls confining stress, and you will think this is S3 being applied on the sample, but because the confining pressure is applied on the core on all dimensions, what you actually measure with the gauge or what you read off from the equipment is actually the differential stress. So it's S1 minus S3, and that's what the result we saw in module 3, where I had asked for the value of S1, and what you did was to add PC to the differential stress. I showed this in the last class, and PC was what is S3, which is equals S2. So So you see how this is how you get S1, because you basically add the confining pressure to the differential pressure. And you can read off all of these, which is pretty straightforward. That's what we do with the triaxial test. Put in the core there, we can compress it axially, and we can apply confining stresses, and we can get more realistic estimates of the rock strength in addition to Young modulus and Poisson ratio.